Characteristic equation. Let A be an n by n matrix and lambda be an eigenvalue of A. There is a non-zero vector x such that Ax is equal to lambda x. That means that the equation, if we bring this one over to the other side, that means the equation Ax minus lambda identity x equal to 0 must have a non-trivial solution, because x is the solution to the homogeneous equation. So what can we say about the matrix A minus lambda x? Well, that matrix must be singular. Singular means that the determinant must be 0. You can think of it this way. So if I have multiplication, this is my one matrix, times another matrix, and that must be 0, since the vector x cannot be 0, to get the 0 on the other side, my left side needs to be 0. So that means, but for matrices it doesn't work that way straightforward, but that's in other words that the matrix must be, that's why the matrix must be singular and the determinant is 0. So that means the determinant must be 0. So if we are okay with that, then we have the definition. The equation determinant of this matrix is equal to 0 is called the characteristic equation of A. So that's the matrix what we have, characteristic equation of A. A scalar lambda is an eigenvalue of n by n matrix A if and only if lambda satisfies the characteristic equation. For each, so let's see the example. For each given matrix, find the characteristic polynomial, its eigenvalues, and the corresponding eigenvector. So to find eigenvector, we would set up that the determinant of this matrix must be 0. That's how we find the eigenvalues. And eigenvectors, we will solve the equation, which is the equation on the right side, A minus lambda x. We need to have the eigenvalues already for a non-zero vector x. So if we find the determinant lambda minus identity x, so we set up the matrix, means we subtracting lambda on the main diagonal. So we have 4 minus lambda, and here we have minus 1, then we have 2 and 1 minus lambda. This must be 0. So cross multiply, solving the determinant, and subtract the other multiplication, and then we solve it. Multiply this out, and then we solve the quadratic equation for lambda. So the equation by itself is called, or the polynomial that creates the equation is called characteristic polynomial. Polynomial lambda square minus 5 lambda plus 6. And the equation, when the characteristic polynomial is 0, the solution to that equation gives us eigenvalues. So eigenvalues for the given matrix are 3 and 2. Then we need to find eigenvectors corresponding to each eigenvalue. So for lambda equal to 2, we will solve A minus 2 identity x equal to 0 for a non-zero vector. So we subtract 2 from the main diagonal of the given matrix. So 4 minus 2 minus 1, 2, 1 minus 2, and this one, the last column is the column of 0 vector, right? Because this would be my x1, this would be my x2, and this would be my number column, right? So then we solve this equation. Then we solve it. So if I solve it, I would need to I'd first simplify, then divide by 2 and add them together. So we have the solution, that the solution is nothing else but we would have 1/2 and 1. So if I factor, then that the solution is right. The solution is right here. So eigenvector corresponding to lambda equal to 2 is 1/2 and 1. Now we repeat exactly the same process to find the eigenvector for this given eigenvalue. So we solve a minus 3 because eigenvalue is 3 this time, identity equal to 0. So in that case, we subtracting 3 from the main diagonal and solve the system. So reduce the matrix to reduced echelon form. And if you solve the system, you're getting the eigenvector equal to 1, 1 for the eigenvalue equal to 3. Now we have next example. So for the given matrix B, first we need to find, first we are trying to find eigenvalues. So we need to set up that the determinant of the matrix A minus lambda identity is equal to 0. We need to solve this equation, right? So what we are doing, we're doing nothing else but subtracting lambda from the main diagonal elements of those ones, right? Subtracting lambda, and that's what we have right here. And this is the determinant, so we keep the straight lines of the matrix. And then if we perform, so to solve, we need to solve the determinant. So for 3 by 3 matrix, it is very beneficial to reduce that matrix a little bit, perform row operations. So if I add the second row and the third row, if I add them together, determinant does not change. You need to pay attention to use properties of determinants. Determinant does not change. So my second row is this, gonna stay as this. My third row is gonna change. And then we keep expanding, solving the determinant by expanding. In that case, I expand by the first column. So if I expand by the first column, I would have this matrix. Maybe I would write. We by the first column we gonna have we would have oh, we would have 1 minus lambda times the cofactor of 1 1 plus, and then we're gonna have minus 3 times the cofactor of the position, which is 2 and 1. So then if we perform and keep expanding, that's what we are getting right here. Minus 1. That's what we're getting right here. And then the what we have, so it's minus is the term 1 minus lambda, and then we have minus 1 to the power 1 plus 1 from the cofactor, right? And then we would have, by deleting the first row and the first column. So this is the matrix that is left. That's gonna be right here, this matrix. And then we're doing the same for the second one. So minus 3, that's right here, minus 1 to the power 2 plus 1. And then we would have, by deleting second row and first column, so what's left is right here. And then by multiplying, so for 3 by 3 matrices, it is very beneficial. Try to keep factoring as much as possible if we can. So first we keep reducing. First we keep simplifying, cross multiplying, and then this would give us 0. So then we try to keep factoring, because then you need to solve it equal to 0. So try to factor as much as possible. So don't multiply this out, just keep factoring whatever it can, because at the end you need to factor and equal to 0. So so this would be my characteristic equation. And if I solve it to 0, those are my eigenvalues. So then we solve for each eigenvalue. We need to find eigenvector. So for lambda equal to 1, we need to solve A minus one one identity. So I'm looking for this lambda equal to 1. And in that case, I'm subtracting 1 from the main diagonal. And we would have, so we're gonna have 0 first here. Then we have minus 3, minus 3. And then we would have 3 on this one, right? Okay, and then we would reduce, perform the row operation, and if you solve the system, you get the eigenvector right here. So this is the eigenvector corresponding to lambda equal to 1. And we proceed exactly the same for lambda equal to minus 2. We're gonna solve this equation for a non-zero vector, and the first would be, I think we cut it right here. So the first is 3 and minus 3 and 3. So I basically have the same. I'm messing with the first row, minus 3 and 3. So if you perform row operations, you would get this, and eigenvectors. We have two free variables. If you solve it, the eigenvectors turns out to be those two. And the same we're doing for the matrix C. To find eigenvectors, first we solve this equation. Actually, for a triangular matrix, we already know that eigenvalues are the numbers on the main diagonal. So my eigenvalues are 0, 0, are 2, 2, and 0. And if you solve it the way we just learned it, you get the same numbers. So then we find the eigenvectors exactly the same. For lambda equal 2, we need to solve this equation. So subtract 2 from the main diagonal. From the original matrix, if we subtract 2, from the original matrix, we would get this equation, and then keep reducing, basically solve it. Try to solve on your own and check the answer, and you should get the eigenvector 1, 0, 0 corresponding to lambda equal to 2. We repeat the process for lambda equal to 0. So we subtract 0 on the main diagonal. We subtract 0 on the main diagonal, so we get exactly the same matrix. Then we try to reduce it. We always need to have free variable, only because that's the definition of the eigenvalue. So once you perform and solve it, you're getting this eigenvector. So this is the eigenvector corresponding to lambda equal to 0. Eigenvalue can be any number, positive, negative, or even 0. And the last thing that we would like to talk here is the similarity. So if A and B are n by n matrices, then A is similar to B if there exists an invertible matrix P such that P inverse AP is equal to the matrix B. So that's the definition of similar matrices. So for similar matrices, if A and B are similar matrices, then they have exactly the same characteristic polynomial. So what that means, that they would have the same eigenvalues. The eigenvalues are the same with the same multiplicities. So here's the justification. Here is the justification of the theorem. So if A and B are similar, that means there is an invertible matrix P such that B is equal to this matrix. So now I would like to see what is B minus lambda identity, because for characteristic polynomial, I need to get determinant of this matrix B minus lambda identity. So B minus lambda identity, I would substitute I would substitute for B first. So B is this matrix, so I'm substituting this, and identity is P inverse times P. Then on the right side, I'm gonna factor P from the right side. So this P is factor from the right side, and P inverse is factor from the left side. Pay attention because matrix multiplication is not commutative. So that means what we did right here. So if I factor P from the right side and P inverse from the left side, I am left with nothing else but A minus lambda identity. And then I consider the determinant. Then I consider the determinant of B minus A lambda identity. This is equal to determinant of this matrix because that's what we show, that B minus lambda identity is equal to that. By properties of determinant, if you have multiplication, you can separate the determinants. And then determinant of P inverse is 1 over determinant P. Determinant is a number, so those two reduces, and I am left with determinant of A minus lambda identity. What that means is that the similar matrices have the same characteristic polynomial, and if they have the same characteristic polynomial, the eigenvalues would be the same. So pay attention to the theorem. The theorem basically says if matrices are similar, then they have the same characteristic, the same eigenvalues. But the inverse is not true, not always true. That means if the two matrices have the same eigenvalues, they may or may not be similar. And that's the first note what we have here. If two matrices have the same eigenvalues, they may or may not be similar. So those two, for example, those two matrices, they have the same eigenvalues because eigenvalues are the numbers standing on the main diagonal, but they are not similar. Similarity is not the same as row equivalence. If A is row equivalent to B, that means to E times A for some elementary row operation. If you remember, if you perform row operation, you kind of multiply times the matrix E, elementary matrix. Row operations on a matrix usually change its eigenvalues. So the original matrix and reduced matrix would have different eigenvalues. So for an n by n matrix A, is invertible if and only if 0 is not an eigenvalue of A. Sometime later we will see how this statement is true. I believe that's everything what we have for this section.